So please watch all the experimental videos because they help you understand how science really works, and there are plenty of helps and hints for your science experiments and Year 12 exams as well in a lot of these videos. So first of all, you're going to see here that the drop counter is far superior to the traditional titration method because it shows you not just the endpoint but the equivalence point, and it is also automated. The problem is first you have to be able to get it to work. So you calibrate both the pH sensor. We'll do that first. And so we've got buffers here. We need a 4 and a 10 in order to tell the machine what the correct reading is. Go to the calibrate button down on the left-hand side. And then once you've done that, you're going to do a 2-point scale. Let it settle down. And then you tell it that that one is correct. That one is the pH 4, and then let this one settle down. I didn't let it settle down, so I just pressed the button a few times when it was press the button again when it was settled. And that one is the pH 10. Let it know that that reading is pH 10. So the next thing you need to do is also calibrate the drop counter. Now I was just doing a really quick method really, and I just got a measuring cylinder, even though in senior science you should never use beakers or measuring cylinders. And so basically you can see I clicked the calibration button, and I took it to 10 mils with a measuring cylinder. Would have been much better to just put 10 mils with a volumetric pipette at the top and let it out, but I was just a bit worried that a drop would be left behind. So you could just take this to the extreme and use like a 250 mil volumetric flask and tell it's 250 and just keep topping up and wait for half an hour or whatever, and that would be super effective. But I'm pretty sure that the rate of flow of the drops also counts, so probably a faster drop has a smaller volume than a larger drop. So you need to control the flow rate as well, and that would be close to perfect if you did it that way, if you had the patience. So the first titration we're doing is just a strong acid and strong base. So first of all, these are the rules of thumb. So other textbooks and teachers have different rules of thumbs, but I'm just trying to make this one easy to remember that covers all the exam questions. So if it's between 1 to 2, it's a strong acid, 13 to 14, strong base. There's a little bit of a grey area you can see. I've got some areas not covered. So plus or minus on the 10 is a weak base, plus or minus on 4 is a weak acid within reason. So we'll see how that goes. So for this one, it's fine. We've got about a 1, so it's between 1 and 2, and it finishes at about 12. So first of all, there's one fault here, and then the mixing's not great. You can see the mixer here it's just a little thing. So probably better off putting a larger magnetic stirrer. Unfortunately, might have to use a larger beaker. So the next thing is this one illustrates to you the difference between equivalence point and endpoint. So endpoint is a pH when you notice there's a change, and you can see here that's at 7. And then at the very end, you can see, and you could take the data values here and do a derivative graph to get that a little bit more accurate. But just taking a crude value, you can see at the top that the amount of fluid gone through is about 25. And so that there you can take the exact readings. Off to the left there are the actual data values I didn't show you. And so you can see clearly there that there is a slight difference in endpoint and equivalence point, and you could crunch the numbers there to get an even more accurate value. And that sort of thing you can't do with just a titration when you've only got endpoint available to you and you don't have all these data values processed. Plus this is automatic and can be done quite quickly many times, unlike a titration. So that's why, and the computers do it. So this is all automated. So this is how the big machines do it, not having a person spend lots and lots of time on it. So this is how it's done now. So what we're looking at here is a weak base and a strong acid. Now you can see if you jump to the end, that it starts at about 10.5. So that is the wheat base, and it ends at about 2. So that is the strong acid. And so if you take the halfway point between that, that's about, I'll draw a line. I haven't drawn a line. That's about 9 mils. The end point, I would say, if I'm just trying to detect a color, even though this thing is not mixing very well, perhaps the end point is at about 7. Let me just drag it off. It's hard to say without the mixing, but definitely 7.5, I would say. And that is probably due to a lack of mixing. Now the indicator, methyl red, if you draw across here, you can see 5.1. So that's in the perfect place for a color change. So 4.4 to 6.2 is perfect. So that is the perfect range for it. How do we know how do we know to choose the pKa, which is 5.1? Why is that the pH at which the color change is the most obvious, or the place where you will see the color change? That you need to be able to explain why an indicator changes at that color. So if I just quickly go to the notes here for an indicator, so what you've got with the indicators is that you can notice the human eye can notice the color change best when there's about half-half. And there's about a 10 times difference in color indicator change with 2 pH units. So you can see that with the methyl red, there is about a 2 pH, 4.4 to 6.2, that around the 5.1 mark. And so if you have half and half indicator and half of the IN minus, you can see that they're equal and they can cancel out. And so that means the Ka is equal to the H plus at that point where it's most obvious that there's a color change. And so if you take the negative logs of both those sides, pK equals pH. So when the pKa is equal to the pH, that is when the colors are equal, and that is when it's most easier to see the difference between the two colors. So that is why you choose an indicator based on where the pH change is going to occur, and make sure the pKa is equal to that pH. So you need to be able to use those equations and write them out and do that little substitution as your description. The description will always need chemical equations in there. Okay, so just a point. These graphs can't be PKBs because the reading is a pH meter, not a pOH meter. If it was a pOH meter, you could just go directly and use that as a PKB. And just going back to this one here, so just drawing the lines in there for the weak base strong acid. You can see at the half equivalence point, it's pretty close to 9.2. And so at the equivalence point, there is none of the weak base. But if you go halfway, there's exactly half of the reactant and half of the product. So the HA or the base with the B plus or the A minus, which in this case. So in that case, when you do the Ka, they cancel out. And so at the half equivalence point, the Ka and the H plus are equal. And so if you do a negative log of both those sides, the pKa of this particular acid or base is equal to the pH. Now that is the pKa in this situation because we're measuring pH. These are the pKa's of the acid. So if you want the pKb's of the acid or the pKb's of the base, then just go forth and use this equation here. So pH 14 equals pH plus pOH, so 14 will also equal pKa plus pKb. So you need to know those equations because they're not clearly written on the data booklet.